also from my side. My name is Markus, I'm from Aalborg University in Denmark, and I'm going to talk today about our paper, Increasing the Accuracy of Low Resolution Commercial Smart Heat Meter Data and Analyzing its Error. And I will jump actually right in with what are actually smart heat meters. I guess most of you are not familiar with that. So we are in the context of district heating. For those not familiar with district heating, that's simplified a way of producing heat centrally and then distributing it to different buildings. Now, within the European Union, every building connected to district heating must have what's called a smart heat meter by latest 2027. What does a smart meter? A smart heat meter measures usually three things: supply flow, supply and return temperature. Based on these three measurements, it calculates, among other things, the total energy used by that building, by that apartment. That total energy usually consists out of space heating and domestic hot water, and these measurements are then remotely transmitted to the district heating company, often on an hourly resolution. So you have an hourly time series representing the total energy use of that building, of that apartment. So what is then actually the problem? Sounds very good, right? And actually, if we focus on the building itself, so where we measure, we actually have a very high resolution. And this is because this is used for billing purposes, so we have a very high quality requirements. And also it is important to know that the energy is measured cumulatively. Obviously, from the cumulative energy, you can very easily calculate the non-cumulative energy, and I will refer to the non-cumulative energy simply as energy use. And this energy use has been shown to be very useful for various applications, ranging from building domain up to district city domain applications. So now, where is the problem? The problem starts here. Utility companies have so far not recognized this value of the data, and so to save cost and to make the data fit what they are used to, they round down the cumulative data to full kilowatt hour. I will also refer to that rounding down as truncation, because basically what they do is they cut everything away after the decimal separator. Now, what's the problem with that? The problem with that is if you now calculate the energy use from that data, you get these on-off patterns for small entities such as single-family houses or for energy-efficient buildings. And that has unfortunately been shown to reduce the usability of this data very significantly, and so far people have not found any solution other than, okay, scale up your resolution, so only consider daily data or something like that, or consider bigger entities. So our aim is actually twofold. We first want to analyze, or we first have analyzed, the error introduced by that process, and secondly, we have developed an approach to mitigate the error and increase the usability and value of the data again. We have done that based on a high resolution data set, data from from 28 nearly zero energy apartments. We have hourly measurements of the energy use of these apartments. Very quickly, we have pre-processed the data by imputing gaps up to 48 values. We have split the data at remaining gaps, so we had a final data set of 166,000 data points / hours. And based on this data set, we have first started to analyze the distribution of the errors. On the top, you can see the error distribution in the cumulative data, and on the bottom, you can see the error distribution in the non-cumulative energy use. So for the cumulative data, we found that for summer months, we actually do not follow as expected a uniform distribution, right? It's what we would expect from the process. And for the energy use, we found this very high number of 0 kilowatt errors. So actually hours where we have no error at all. Both of these things can be attributed to hours where we have actually no energy use in the apartment. What happens if you have no energy use over like several hours is you have repeatedly the same value transmitted. That means you have repeatedly the same error in the cumulative data. That shifts away the error distribution away from a uniform distribution, while these repeated measurements still have no error in the energy use data, right? Because any repeated same value has a difference of 0, and this is what we would also expect in the actual data. We could also prove that very easily by simply removing all the hours where we have actually no energy use in the high resolution data, and then we can see now that all the errors in the cumulative data as expected follow a uniform distribution. And more importantly, for the non-cumulative energy use data, we can now see what is roughly a normal distribution for winter months. Majority of errors here between plus minus 0.5, 0.4 kilowatt hours, For the summer months, we could not really see a clear theoretical distribution, and this is we hypothesized because of the different energy use. Winter, space heating and domestic hot water, summer, domestic hot water only. Based on this analysis and better understanding of how this error is introduced and how it is distributed, we started to develop our algorithm to mitigate this error and hopefully increase the usability of the data. It's a three-step procedure. It's actually quite simple, and this is also necessary because we talk about huge amounts of data we must be able to process. So first step is we smooth the data. This smoothing mainly has the idea of mitigating the effect of these on-off-like patterns we introduce. Secondly, we know from the process how this data is transmitted that in theory we have this accuracy of plus minus 1 kilowatt hour. So after the smoothing, we should never deviate more than plus minus 1 kilowatt hour. And actually from the analysis, and I will talk about this also a bit more in a second, we hypothesized that obviously it might be better to choose a bit tighter bound to limit here the deviation. Thirdly, we scale the data. We scale the data simply because the rounding error is constant. So if you take a larger data period, the relative error introduced by rounding becomes smaller, and so we ensure that our process over 1 year or over some defined period always sums up to the same amount of energy, so we don't introduce here any bias. We have actually then tested this approach with various smoothing techniques, with various settings, as well as with different maximum pointwise deviations. We have always evaluated this in terms of normalized root mean square error and Pearson correlation coefficient. And we have done that not only for our data set entirely, but also for the data set split up into summer and winter, so that we see if we have here any preferences in terms of different seasons where we have before seen that errors might be differently distributed. Overall, we have seen consistent results across all these three analyzed data sets or subsets, as well as across normalized root mean square error and Pearson correlation coefficient, and that is that a simple moving weighted average with a window size of 5, a centered window with a linear weighting, and a maximum pointwise deviation of plus minus 0.4 led to the best results. We always scaled the data per day. Why per day? Well, it's a nice unit, so it makes processing a bit simpler if you have a natural unit like a day. Also, usually over 1 day, the energy use is high enough so that the relative error introduced by rounding is considerably small. If we analyze now the performance in a bit more detail, we can actually see that over the whole data set, we were able to reduce the normalized root mean square error by 0.2 and increase the Pearson correlation by 0.03. If you look at these two graphs, these are simply two exemplary days. We are quite successful in reducing these on-off patterns. So the violet curve, that is what usually is available at the district heating company. The green is what we obtained, and the black line is what is originally actually measured at the building level. Further, because of this threshold of plus minus 0.4 kilowatt hours, we also prevent that we smooth out any peaks, which is important because total energy use usually has quite high peaks due to domestic hot water. So we are both successful in getting a more smooth behavior when we have what is probably mostly driven by space heating. At the same time, we prevent that we get rid of any peaks produced by domestic hot water. We have then also analyzed the performance compared to our actual data, so how our method basically performs compared to the accuracy of the truncated data. How we have done that is quite simple. We have used the truncated data and calculated Pearson correlation coefficient and normalized root mean square error compared to the high resolution data. Afterwards, we have processed the data, evaluated the data again after processing. And then we can see now this clear correlation for the different days between the performance after we have processed the data and before it was processed. This means that, and this is to be expected, if you have a large loss of information, if the truncated data has very little to do with the actual energy use, we cannot magically make this information reappear, but we can improve it overall. However, we can also see that it's not true for all days, right? We have some days where we actually make it slightly worse for both the normalized root mean square error as well as the Pearson correlation coefficient. I guess that's a thing we need to live with. but overall the positive effect exceeds the negative one in quantity and magnitude. And yes, perfect. So overall we can conclude that our method can reduce the rounding error, but it cannot completely overcome it. So we have to create proof now that there is really a need for your district heating utility companies to act, to recognize the value of this data beyond sending a bill once a year to a customer. And really there is a need to increase the transmitting resolution of commercial smart heat meters. Thank you very much.